In this video, we're going to try to do ray diagrams for concave mirrors and explore all the different cases that exist for these mirrors. So we're going to start off with the first case, which is where you have an object placed in between the focal point and the center of curvature. So for example, if this is 5 centimeters away here, this is 10 centimeters away, and so this is somewhere in between 5 and 10. It doesn't have to be exactly in between, but it could be somewhere between 5 and 10. So the first thing that I do to find the image is I make a ray that goes parallel to the principal axis until it hits the mirror. And according to our special rays, that will reflect so that it goes through the focal point. And you have to be very precise, make sure that this is parallel here, and make sure that it actually does go right through the focal point. The next ray I'm going to choose to do is one that goes through the focal point, hits the mirror, and then it's going to reflect parallel to the principal axis. So you'll notice that I put my arrows there to show it's going into the mirror. It's going to reflect parallel to the principal axis. Make sure it is parallel. Don't go too far up that way. So make sure it is actually parallel to the principal axis. And this point here where they meet, where these rays meet, that's where the top of the image is going to be, because these points came from the top of the object. So that's where the pencil top will be. The pencil tip here will be. And so if that's the pencil tip, then the eraser will remain on the principal axis. So I always have the object on the principal axis so that the base stays there, but then the pencil tip ends up somewhere else. So you can draw, this is your pencil, this is the pencil tip, this is the eraser over here, okay? And just to repeat that process there, we have parallel to principal axis through the focal point, then through the focal point, and then parallel to the principal axis. You could have chosen other rays. You could have done one that went to the vertex, and then you measure the angles, and it would have intersected there as well. You could have done one that went through the center curvature. So in theory, one that comes out through there reflects back on itself, and it would have met there as well. But only 2 rays are needed, so there's your image. And what you'll notice is that the image, the HI, is greater than HO. So if you were to measure HO and measure HI will be larger. You'll also notice that the image is no longer upright. It's now pointing down. This is pointing up, and this one's pointing down, so they're flipped compared to each other. So the image is considered inverted. You'll also notice the location is different. If you want to measure DO, the object is between F and C, so you could measure from here to get your DO, and your DI you'd measure from the vertex to the image. But if you wanted a quick little description, you would say that the image is beyond C. It's farther away from C. So it's farther away from the mirror than the object was. And so those are different ways to describe it. But you can also measure it with a ruler. And lastly, the type. You'll notice that the image is actually made from real rays. There's no tracebacks in this situation. It's real rays that made the image. So the image is actually in front of the mirror and made by real rays. So we would call that a real image instead of a virtual image. So whenever you have the object in between C and F, the image is going to be farther away from C, inverted, larger, and real. And so you can show that with ray diagrams, but you could also sort of memorize that idea. And it'll make more sense as we do more examples with other cases as well. So you can pause the video and try this one out on your own. It is important to be precise. You're going to use the same set of rays and try to see where your image forms. This is the case where you are at C or at 2F. So if this is 5 centimeters, this is 10. Your object is placed 10 centimeters from the mirror. Now, I just made up a number here. This could have been 8 centimeters and this is 16. It doesn't matter. The point is that this distance here is double this distance here. So I do one ray parallel to the principal axis. That goes through the focal point. And make sure it's through the focal point. This is hard to get exactly through it because that dot's so big. The smaller the focal point, the easier it is to draw right on that focal point. Then I do one through the focal point and then parallel to the principal axis. So through the focal point, parallel to the principal axis. Here's the tip of my pencil. The eraser stays on the base, on the principal axis. And this is my image now. So this is probably one of the easiest ones to remember because when you're on the center of curvature, the object, the image is on the center of curvature as well. So DI is actually equal to DO in that situation. You'll also notice if you measure this object, HO, and measure this image, HI, they're actually the same. So HI is equal to HO. The only thing that's interesting, that's odd about the image is that it's flipped, so it's inverted. But it's the same size, same distance away, but inverted for the orientation. You'll also notice that it's made by real rays again. So because it's made by real rays again, and it's in front of the mirror, we have a real image. So that's our description using lost. And again, one of the easier ones to remember because it's simply on the center of curvature, but inverted. You can try this next case out as well. This is a case where the object is beyond 2c. So if this is 5 and this is 10, this is somewhere beyond 10. I shouldn't say beyond 2c, I misspoke. I meant beyond 2f or beyond c. 2f means c, right? Because 2 times f is the center of curvature. So, same set of rays. One parallel to the principal axis through the focal point. Make sure it's through the focal point. One through the focal point, parallel to the principal axis. And there where the real rays meet, that is where our image is going to be. So, at a quick glance, you notice that the image is not as far from the mirror as the object. The object is this distance. The image is only this distance. The image ends up somewhere in between C and F. You can measure that specifically, but DI is less than DO, and the image is somewhere between C and F. So that's kind of our pattern or trend there. If this is outside of C, beyond C, then this image ends up somewhere between the two. It is inverted. If you were to measure this, this is slightly smaller than this pencil here, so the HI is less than HO. And again, it's made by real rays, so it is a real image. Next, I want you to try this one out. So you can pause the video and try it yourself. A little hint, make sure you trace all your steps. Trace all your steps. So if you tried this and you got lost, no pun intended, you probably did not pick up on the hint of trace all your steps. So let's take a look at this. This is a situation where the object is placed in between F and the mirror. So let's say this is 5 centimeters. This is somewhere less than 5 centimeters away from the mirror. Okay, so inside the focal length. So I would start off by doing the same first ray, parallel to the principal axis, through the focal point. Now, the other one's kind of tricky to do. There's a few you can do. You can do one that goes through the vertex, measure the angle, and then go through the vertex again. So you can do that. But you could also do one that looks like it's coming through the focal point. So you take your ruler, put it here, line it up, and then make sure it looks like it's coming out of the focal point. Okay, this is a bit off. I think this should have been a little bit higher up there, but it has to be coming through the focal point. You don't have to draw that part, just draw that part there as if it came through the focal point. And that will reflect parallel to the principal axis. Some students also do the one that looks as if it's coming through the center of curvature, and that just stays on itself. But the point that you'll notice is that this reflected ray and this reflected ray, they don't meet. So if they don't meet, where's the image? Right? It looks like there's no image there. But remember, trace your steps, trace backs. So if you make a trace back of this and a trace back of this, you get your image over here. So when you're inside the focal length, in between F and the mirror, do your rays, and then at the end, do trace backs of your reflected rays. And where the trace backs meet, that's where your image is. So you'll notice that your image is actually upright this time. It's behind the mirror, so it's made by trace back rays or virtual rays, so it's virtual. You'll notice it is a lot larger. So if you look into a curved mirror, concave mirror, up close, you'll see you look a lot larger. And you'll notice you're farther away from the mirror as well. This one's probably the one that throws students off the most because they forget about tracebacks. Don't forget about those tracebacks, and you should be fine to do questions like this. The last case is the second easiest to remember, I would say. When the object is at the focal point for a concave mirror specifically, not a convex mirror, or a concave mirror specifically, there's no image. You'll notice that when you do your ray parallel to the focal, if you want to do one through the center of curvature, you can. If you do one through the vertex and then measure the angle and then do your reflected ray, these rays don't meet. So you might think, well, you just taught us about tracebacks, so make your tracebacks. But what you'll notice is that these rays are parallel. So that they're not even angled towards each other, so their rays will never meet. Or they're not even angled away from each other, so their tracebacks will never meet. So when you have an object that's placed at the focal point, it'll become blurry and not even form an image because the reflected rays end up being parallel to each other and they never meet either on the side, on the front of the mirror or behind the mirror. So that's important to remember for a concave mirror, an object at the focal point. So if this is 5 centimeters away, the object is 5 centimeters away, will not have an image form. So this is a summary of all the different scenarios that we saw where the object is placed. So beyond C or beyond 2F, at 2F or at C, between C and F, at F, and inside F. You can see all the different image characteristics summarized for you here along with the pictures. What's important is that you practice those different scenarios on your handout over and over again until your drawings match what's expected and until you internalize what it means to be at the different sections and where roughly your image should end up. So we're going to take a look at some applications of concave mirrors. So before you jump into these applications, it's important you understand how to draw concave mirrors, ray diagrams, but let's try some application problems related to applications of the concave mirror. So you'll notice here that there's several applications. There's more than just this that exists out there, but we have the flashlight, the telescope, the cosmetic mirror, and the headlights of a car. So if you look at the flashlight, you'll see here that you have a light bulb in the middle there and a concave mirror surrounding it. The light shines and then the light hits the mirror and all the rays jump out parallel to each other, roughly parallel to each other. So that being said, if all the rays jump out roughly parallel to each other, where is this light bulb placed? Hopefully you had time to think. Remember the case where you have light that goes through the focal point, reflects parallel to the principal axis and to each other. So this light bulb is probably placed at the focal point to make it so that the beam comes out in a parallel with a bunch of parallel rays. It's used in some telescopes as well. So you can see here light comes in from the celestial object you're observing from far away. These rays are parallel to each other because the light's coming from so far. You can see that it hits a concave mirror here, and that concave mirror causes those parallel light rays to meet at this mirror, and then your eye would be here so you could see what you're trying to observe from up here. But think about how I know this is concave. It doesn't look particularly concave in the drawing, but if you think about it, using your knowledge or application, when the light rays are parallel to each other and they hit that concave mirror, they meet at a point, and that point's your focal point. Cosmetic mirrors, basically makeup mirrors, you can open them up. When you look inside, you look larger. So if you're close to that concave mirror, you're upright and larger. So that's an example of a concave situation. If you think about this situation where you're a cosmetic mirror and you're upright and larger, think about where you are compared to the focal point. That's another part of the application as well. So if we look back at our scenario here, when you were in between F and the mirror, the image was larger and upright. So for the cosmetic mirror to work, you have to make sure that you're in between the focal point of the mirror and the mirror so that you're upright and larger. Here we have a solar oven. So the solar oven you can see is a concave dish mirror, and we put our food here, and parallel sun rays would hit the dish and then focus onto the food. So think about where you'd want to place your food relative to the different parts of the concave mirror for maximum cooking. And so yes, if you guessed it, if you guessed at the focal point, you're correct, because that's where the light rays would be focused to if they were parallel to each other coming in from the sun, and they could heat up the pot of the food inside the pot here. Think about if we go back to, so we answered most of these questions here. So when enlargement of image is needed, where would the object be relative to the focal point? So we just explained that now for the cosmetic mirror. Where should you place food in a solar oven? Explained. So we just described that here as well. A telescope lets you see a smaller image of space. Where are the celestial objects relative to the focal point? Explained. So I mean, this one's, you could answer this in two ways. if you're looking at objects in space, those are very far away, so they're probably going to be larger. They're probably going to be farther away than the center of curvature. But you're able to see smaller objects that are from space. So because you're seeing smaller objects, usually you see smaller objects when you're smaller images. Usually you see smaller images when your object is beyond the center of curvature. Then where's the bulb placed in a flashlight? The goal is to produce parallel rays, so we already talked about that. The headlights of a car work very similar to a flashlight with a light bulb and then a concave mirror to allow you to produce a parallel beam. So these were applications of concave mirrors, but what's important to understand is that if I give you an application that's not on here, you can logic your way through how it might work using the different scenarios that we saw for where objects can be and the types of images that are produced depending on where the object is. So at F, beyond, between F and C, beyond C, between F and the mirror. So you have to figure out what case allows a certain application to work, just like we saw in these practice problems here. And if you've been paying attention, this joke is one of the best jokes for optics, so keeping it real. If you can explain this joke, it means you understood the idea of real image and concave mirror. To summarize this lesson, it's a good idea to do an example of a ray diagram with some rules written out for how you can draw ray diagrams for concave mirrors, along with a salt description or loss description. It might be a good idea to summarize the different cases that we saw for the concave mirror, along with some applications and explanations of those applications. A great video to watch is this video here. This is a demo that's done with a concave mirror. It's a really neat concept, and if you can explain this demo, you truly understand all the cases that we saw for concave mirrors.